Hello, welcome to everybody. In today's class also we will continue the Gauss law and its applications. Okay, in the yesterday's class we covered completely about the uniformly charged sphere. Just we introduced about the infinite charge sheet. The topics of today's class are infinite sheet of charge and infinite cylinder. We are going to apply the Gauss law in these two specific cases. In both cases, we want to find the electric field in and around these charge distributions. Okay, right. First of all, let us go for the infinite sheet of charge. Okay. Now, in a different slide, I will show you the infinite sheet of charge. Now, before going to derive the electric field intensity of the infinite sheet, you see here, this is the infinite sheet of charge, now which we are seeing in this slide. You see this is the infinite sheet of charge. Of course, you are seeing this as a finite sheet here, but actually what we are considering here is infinite sheet of charge. What is the reason why we are considering infinite conductor instead of considering the sheet with limited dimensions? That will simplifies our problem. In this case, the field will be so simple. Field will not be complicated in this particular case. That's why we consider the infinite sheet of charge. Actually, the edges in the edges of this sheet. So in the diagram, we have to show the curly edges of this plate. Okay, here the edges are shown. That shows you that this sheet is of infinite extent. Okay, that change you have to notice here. But we are making use of this diagram here. Right now, you see the sheet of charge. Okay, it is something like a rectangular plate, but its dimensions are infinite. Okay, if you are placing this in the xy plane, so here x tends to infinity as well as y tends to infinity. Okay, right. This is infinite sheet of charge. Here we have to apply Gauss law in this particular case. Okay, here the question does not arise in and out, electric field inside and electric field outside. Why? Because the sheet is very thin. But the question may arise, what will be the electric field on the right side of the plate if it is placed in the vertical plane, if it is placed in the vertical plane. Okay, if your plate is perpendicular to the horizontal plane. Okay, then you may ask, what will be the electric field on the right side of that plate? What will be the electric field on the left side of that plate? Just you are placing that plate along along say z axis. Okay, z axis. Okay, in the vertical plane, you are placing that plate in the vertical plane. Then you may ask, what will be the electric field to the right of that and to the left of that? Okay, on the positive x-axis and the negative x-axis. Okay. Now the situation is different from that of the uniformly charged sphere. Okay, yeah. Now let us consider this infinite sheet of charge for the application of Gauss law of electrostatics. Okay, already we completed 3 applications. It is a fourth one. What is this? Infinite sheet of infinite sheet of charge.
Infinite sheet of charge. Okay.
Now here also we have to define the problem. Initially, see, you have to consider a plate. If you are taking some plate, what will be the dimensions of that plate and how much charge is placed on that plate. Okay, you have to assume all these things in order to apply the Gauss law of electrostatics. Okay.
Right, now let us take the infinite
Sheet of charge. Okay.
Otherwise, you may draw here a curly line here and here. This will show you
The unlimited extension of this sheet of charge.
okay. Right.
Now, here actually you want to know the electric field on this side and this side, left and right sides of this plate.
Suppose you want to know the electric field here. Suppose that you want to know the electric field here.
Then what you have to do in the Gauss law, for the Gauss law application, you have to draw one imaginary surface. Now, our question is, what will be the shape of that imaginary surface or the Gaussian surface? Okay, that shape should cover this point as well as this point. Okay, so your option will be circular cylinder. So we are imagining the Gaussian surface to be a circular cylinder which is equally spreading on both sides of this plate. Okay, it is something like that. You are erasing your pen across the paper. This is a paper. So half of the pen is on this side, half of the pen is this side. Your pen is nothing but what is that? Circular cylinder. Circular. It is a circular cylinder. Half of its length is on positive x-axis. Half of its length is on the negative x-axis. Okay, it is spreading equally on the both sides of that infinite sheet of charge. Okay, right.
Before that, let us define the problem.
See here, its dimensions are infinite.
Okay.
So what we have to consider here, after dimensions, what we have to define? Distribution of charge. It is a plate, two-dimensional object. So which quantity describe the charge distribution on this plate? Surface charge density. Okay. Now let us assume that
Let the charge, let the surface, let the surface charge density of the sheet be sigma.
small sigma. Okay, this will give you the distribution of charge over that sheet, two-dimensional object. Okay, it is enough for us. It will give you the charge, okay, on the plate.
Okay. Right.
Or charge distribution on the plate.
Right.
Now you want to apply the Gauss law to know the electric field both on right and left sides of this plate. Okay, for that we have to imagine the Gaussian surface.
See, you want to know on this side as well as on this side.
Your Gaussian surface should pass through these 2 points. Okay, so most obviously we consider the Gaussian surface in the shape of a circular cylinder. Okay, one point will be on the top of the cylinder, one point will be at the bottom of the cylinder. Okay,
Now the cylinder is passing through.
now the cylinder, you see in the slide also, the cylinder is piercing that plate. Okay, just we are imagining. Okay,
Right. Yeah. Your point is here. Okay. Say this point P. Another point is here at the bottom. Okay, at the bottom.
Okay. You see this line on the slide also. Okay. Right. Now this is your Gaussian surface. Okay, even though I am drawing the thick line. Okay, it is a Gaussian surface. Now your Gaussian surface is in the shape of a circular cylinder. Now you may take the, you have to define the base radius for this. Okay, let the radius, base radius of this circular cylinder be, let base radius of the cylinder be how much? R. Okay. Say this point, another point, you may call this as P point, whatever you like. Okay. Right. Now, yeah, here the sigma is the distribution of a positive charge. Okay. Even though I am not mentioning here, it is a positive charge distribution. Okay. Now you may put pluses here on this plate like this. Okay. Then what will be the direction of field? Field lines will emerge from this plate to both left and right side. So this will be the electric field now. Okay. These are the electric field lines due to the charge on the infinite sheet of charge. Okay. Now you see this cylinder, imaginary cylinder is perpendicular to this plate. See, this is your plate, your cylinder is going like this. Half of it is on this side, half of it is in this side. Okay, it is passing through this infinite sheet of charge or plate. Okay, right. Now we have to apply our Gauss law to this imaginary Gaussian surface. Okay, okay. First of all, let us consider. Yeah, what is the what is this surface? This is a ds. Okay. This patch is ds. Okay. This is also ds. When it is ds, it is also ds here. Okay. What is ds? This portion. Okay. Yeah. Now, what will be the direction of ds here? This is the direction of ds vector. Here also, this is the direction of ds vector. ds vector. Right. Now, we have to apply Gauss law for this cylinder. Okay. Now, according to the Gauss law, according to the Gauss law, just write down it as it is. Integral E dot ds is equal to q by epsilon. Now you have to apply, you have to modify this Gauss law according to your problem. You have to manipulate LHS as well as you have to manipulate RHS. Because you want to apply this law for this particular problem. Okay? Right. Here Q is not mentioned for us. We did not assume Q. So we are only given sigma. So we have to express Q in terms of sigma. Okay, that you know very well. That you know very well. Because you are having one formula for that. Okay? Right. Here, now, let us write EDS first. Let us modify this EDS. Later on, let us modify that Q. Okay. Later on, we will write what is Q here. Okay, this is ds. Right. Yeah, here what we have to write? Integral vector E. When you expand the dot product, you have E modulus ds cos theta. So this is ds, this is E. Both are parallel. So for these two patches, top and bottom areas, E and ds are parallel.
Then you have 0.
Okay.
Theta is 0. Okay.
But how many surfaces are there? 3 surfaces. Top and bottom for the cylinder. Next, lateral surface is there. Lateral surface is there. If you take any, see here, if you take a part of, if you take a patch on this side, on this curved surface,
Then if it is ds, then what will be the direction of ds here?
what will be the direction of ds here? Upwards. Okay. What is the direction of electric field? Horizontal. So in this case, theta will be 90 degrees.
So we are writing
EDS cos theta for this surface and this surface. Okay. In these two cases, it is said.
why? Because on this side also your ds is
Parallel to
this E vector. Why? Because on this side also you have field lines like this. Okay, on this side also. So how many parts are there in this integration? For this surface, one integral you have to calculate. For this surface, you have to calculate one integral. For this lateral surface, you have to calculate one integral. So you are splitting this integral into 3 parts. Why? Because you have to go through all the surfaces, then only it becomes a closed surface. You cannot apply for the open surface, Gauss law. That's why you cannot ignore this. Okay, you have to consider all the surfaces which are making the surface closed. That's why, yeah, this is for say this ds. Okay, for another surface, suppose that this is top. Same situation prevails at the bottom also. So what you have to do here? Plus one more. You have to write one more. Here you need not to put circle now because we are splitting that integral. Okay. E ds. Here also cos 0. On this side also E is parallel to ds. Okay. Next, plus here I am writing plus this lateral surface where ds is perpendicular to E. That means theta is 90 degrees. This is ds. This is E. Okay, theta is 90 degrees. Integral E ds cos 90. Okay. Now this LHS part is over. Okay, this diagram is different. You need not to combine this with this derivation. Okay, yeah, this integral is equal to sum of these 3 integrals. On this side, what you have to write? What is Q? Here, Q is, yeah, whenever you express Q in terms of sigma, what you have to write? Q is nothing but integral sigma ds. You may also write Q is equal to rho dV, but we can't write here. Why? Because we are dealing with a 2-dimensional problem and we are already assumed sigma. That's why I am expressing Q in terms of sigma. Okay, sigma ds. Okay, right. Now, yeah, I am erasing this part here. Okay. Now you see here I am writing here. What about this first part and second part? Cos 0 is 1. We need not to write anything here. Here also cos 0 1. Here cos 90 is 0, means third term altogether vanishes. So we are only left with integral EDS plus integral EDS. That means how many integral EDSs you are having? 2. So on this side you have only integral 2 E ds, okay, is equal to On the RHS side, what you are having? Here, you have to write epsilon naught also. Why? Because EDS is equal to Q by epsilon naught. Na? Yeah, you have to write epsilon naught here. Okay. Integral 2 integral E ds is equal to what you are having on this side, sigma ds by epsilon naught. Sigma ds by epsilon naught. You see, here also E is constant. E is a constant. Why? Because see, for all the points on this plane, or for all the points on this plane, E is constant. Okay, it is also symmetrical object. It is dividing the space into two equal parts, your plane. So our problem is a symmetrical problem. Here also E is a constant. That means here you comfortably write E outside of this integral. If that is not the case, you cannot simply write it outside. That will be totally wrong. Okay, so we apply the Gauss law only in such cases. That means in such symmetric objects. In case of such symmetric objects, that is very important thing here. So when E is constant, you may write E outside of this integral. That means you are having E. See, whenever you are having modulus and that arrow mark, we need not to write anything in the next step. Let's simply write E. Why? Because that is the magnitude of E, that is a number. Okay. Yeah. Now we are finding the magnitude of E only by applying the Gauss law. Right. On this side, what you are having? ds. Okay. ds. Here also you need not to write anything. This is also a scalar. Okay. Now magnitude of the ds vector. This is equal to, yeah, here sigma is a uniform charge density. Wherever you go, this will not change. For every unit area, you will find the same charge. So you can comfortably, okay, it is a constant characterizing that plate, charge distribution on that plate. Here also you may write the sigma outside, just you will get integral ds here also. Yeah, and now you can see here, after this step, what you have to write? See, on both sides you are having sigma ds. That is a total area. It is a total area. So simply now you can write this as, now simply you can write this as 2E is equal to, 2E is equal to, otherwise I will write here 2E is equal to, on this side what you are having, sigma by epsilon, sigma by epsilon. So what is your E now? Therefore E is equal to how much? You are getting sigma by 2 epsilon naught, sigma by 2 epsilon naught. So this is your final expression. This gives you the electric field intensity on both sides of the infinite charge sheet, infinite sheet of charge. What can you understand by this formula? What do you understand with this? You got this formula now. What is the meaning of this? Is there any variable? Something like R? Of course, this point may be located at a distance R. This point is also located at a point at a distance R, or it may be located at okay, R1, R2. But we are taking this to be R, this is also R, but there is no R in the expression at all. There is no R in the in this expression at all. What is the meaning of this? See, your field intensity only varies with this sigma. If you increase the sigma of the plate, if you increase the surface charge density on the infinite charge sheet, then you will have more electric field intensity on both sides of that sheet, both sides of the sheet. If you increase the charge in the unit area, then most obviously you have you have high field on both sides of the infinite sheet of charge. Field intensity increases as you increase the sigma. That is what our conclusion. That is what the physical meaning of this formula. Now, what can you conclude from this? So, on both sides of the infinite charge sheet, field intensity does not varies with the distance of that point from the plate. Distance of this point P from the plate. You may locate P here, you may put P here, or you may put P here. But the E will be the same. E will be the same. But when it changes, it only changes when you alter the charge distribution on the plate. If you increase the surface charge density, then electric field intensity at this point will be somewhat more than the previous case. Okay. So electric field intensity is only a function of charge distribution. Okay, in this case, right. So this applies to both right and left sides of the plate or sheet of infinite sheet of charge. Why? Because both are symmetrical. Both are symmetrical. One is on either this side, another one is on the other side of the plate. Okay, because this is a symmetrical problem. So, electric field intensity of an infinite sheet of charge will not depend on the distance of point from the plate, perpendicular distance of the point from the plate. It is independent of variable r. Okay, it only depends on the charge density of the plate. Charge density of the plate. So here this sheet of charge is extending up to infinity. Why we are imagining that infinite sheet? Then only this formula will be correct. Okay, wherever you go. Okay, this formula will be correct. Otherwise, if it is of limited dimensions, if it is having the limited dimensions, okay, whenever you go upwards or downwards or sidewards towards the edges, then your electric field will not be described by this formula. Okay, fluctuations in electric field takes place. It will not be uniform. Okay, that's why we are taking infinite charge sheet. Even though practically taking this is not possible, okay, you may consider a very large plate, but not the infinite sheet of charge. Okay, from the theoretical point of view, we considered this thing, this infinite sheet of charge. Right. If it is not the infinite sheet of charge, your formula will only applicable in the middle portion of that sheet. That may be on right side or left side, on the right side or left side. Okay. Right. Now this is about the finding of electric field intensity of an infinite sheet of charge by using the Gauss law of electrostatics. Gauss law of electrostatics. Okay. Yeah. Now let us go for our another application. What is that? I already told you that at the beginning of the class. That is cylindrical charge. That is cylinder, charged cylinder. That is charged cylinder. Okay. Charge, otherwise we may call this as charge circular cylinder. Okay. Now already your cylinder here is imaginary one, but we are going to make it real. This is your object here. In the next example, this will be your object. It will not be the imaginary. That is what the change. From this problem to that problem. We have to take care of that. Right. Now I will show you the circular cylinder in a different slide. Yeah, now you can see the infinite circular cylinder. This is also infinite object. Okay, we are considering its longitudinal dimensions to be infinite. Okay, right. Yeah. Now you can see this here. Okay. Yeah, this is infinite circular cylinder or charged cylinder. Okay. Now, for this charged cylinder, we have to apply the Gauss law of electrostatics. Okay. Here we are imagining that this is spreading along the y-axis up to infinity. That's why we call this as infinite circular cylinder. So why we have to consider this object to be infinite? I already told you that. Okay? The reason is the same as in the previous case. Okay. Right. Now let us go for the second example of today, second application of today. So, wherever you go, the field intensity is not changing in the previous problem. In case of infinite sheet of charge, that means electric field around the infinite sheet is uniform. That's why its value is not changing, even though you change your point of observation on both sides of the sheet. Okay, that you have to note. Right. Now, we are going for the second example of today, infinite circular cylinder. Okay, again we will do the same thing. We will formulate the problem, then we will try to apply the Gauss law of electrostatics. Yeah, here you see this cylinder is spreading along all the three directions. That you have to note. It is a three-dimensional object. Okay, so now it occupies some space. Okay, it occupies some space. You may be interested in knowing the electric field in that space. That means inside the cylinder. Here, two cases arise. Okay, what are those two cases? You may be interested in knowing the electric field inside the cylinder, or you may be interested in knowing the electric field outside the cylinder due to the charge distribution on that cylinder. If there is no charge, then you will not be having any field either inside or outside of the cylinder. Okay, that is also known by the application of Gauss law of electrostatics. Whenever you make Q is equal to 0, flux will be 0, so field will be 0. That is a known fact. Okay, right. See, we are having the electric fields here due to the charge. Charge is the source of the electric field. Okay, right. Now, let us formulate the problem. What is that? Infinite circular cylinder or charged cylinder. Infinite charged cylinder. Infinite charged cylinder. Okay, first let us draw the diagram. See, this is the top portion, and this is the lateral surface. This is the bottom portion of this cylinder. Okay, just reduce the dimensions. Of course, what I am saying here, it is an infinite cylinder. Infinite cylinder. That means here you just draw the dotted line, and this will show you that it is of infinite extent. Okay, infinite extent, right? Yeah. What is this? This is the center of the top portion. This is the center of the bottom circle, bottom portion. Okay, this is the axis of the cylinder. This is the base radius of the cylinder. So let us call this R. So here its total length goes to infinity. We are not interested in that because it is infinity. Yeah. Now your charge is uniformly distributed along this volume, along its volume. Okay, charge is uniformly distributed over this cylinder. It is not laying on the surface only. That you have to note. Okay, right. Here it is all R. Here also base radius will be R. Okay, right. This is the height. Height is going to infinite. Okay, right. Now, yeah, let us consider a cylinder with it is a three-dimensional object, so you have to consider volume charge density. Okay, let us consider the cylinder with the rho volume charge density. Rho volume charge density. What will be the base radius? Let us assume that R be the base radius of cylinder. Okay, now we formulated the problem. This is a real object. This is the real object. In order to apply Gauss law, in order to find the electric field inside and outside of this cylinder, what we have to do? We must have to draw Gaussian surface. Gaussian surface is always a closed surface. It is always an imaginary surface. Okay. Without imagining this surface, you cannot apply the Gauss law. Okay. It is also symmetrical object. That's why we are applying Gauss law of electrostatics. Okay. Yeah. How many cases are arising here? Field inside the cylinder, field outside the cylinder. Okay, to find the field outside the cylinder will be easy comparatively. That's why we consider this as a case A. That means for outside points. Let us consider case A. Outside points. That means field at outside points. Okay. Yeah, now what you have to do? You have to do a specific Gaussian surface. Okay. Right. Now I am drawing the Gaussian surface here. I am erasing this. Yeah. Now go for case A. Field inside the cylinder. Inside or outside? At first we are considering outside points. That is, mathematically you may field at outside points. Okay. Write this as, okay, first of all you draw the, if you want to know the electric field outside the cylinder, you have to draw Gaussian surface passing through that point wherever you want to know the electric field. Suppose that you want to know the electric field here. Then what you have to do? You have to draw an imaginary closed surface. What will be that imaginary closed surface here passing through these 2 points? Cylinder covers these 2 points. So now the shape of your imaginary surface is also the shape of the real object, that is cylinder. Okay, now I will draw an imaginary cylinder passing through these 2 points of interest. Okay, this one here. Okay. You need not to consider this to be of infinite extent. Original cylinder is extending up to infinity, but it is not extending up to infinity. Say its length is only L. Its length is only L, or height, if you call it as height, say small height. Okay. Right. Now, what is its radius now? Base radius, say this is small r. Why? Because you are considering a point situated at the distance small r. Okay, you want to know the electric field intensity here at this point. Say this is your P. Okay, at all the points on this surface and on this surface, at all the points on the lateral surface, you have the same electric field intensity. Why? Because all those points are located at the equal distance, that is radius, from the axis of the cylinder. Okay, here also your E is constant over this surface, lateral surface. Okay, right. Yeah. Now, how to show the outside points mathematically? This is your R now. This R is greater than this R. Small r is greater than capital R, radius of the cylinder. Okay, this will give you the case A, that means field outside the cylinder. Okay, right. Now let small r be the base radius of Gaussian cylinder. Gaussian cylinder. Okay, it's let its length be small l. Okay, now we formulated the problem. Okay, we have drawn the original object, we have drawn the imaginary surface, we fixed the dimensions of the object as well as imaginary surface. Okay, now we have to apply Gauss law. Yeah, by using the Gauss law, okay, now I am removing this, otherwise I will write here. Yeah, according to the Gauss law, what is Gauss law? Integral E ds is equal to q by epsilon naught. Okay. Now we have to modify this formula based on our problem, that is charged cylinder. We have to apply this formula for this. See, what is q? It is a general formula. What is the q in our particular case? That you have to find. How much charge is there? Here charge is not given in the problem. Okay, volume charge density is given. That means you have to express the charge in terms of volume charge density. Okay, then what happens here? What happens to this RHS? Q is a integral rho dV by epsilon naught. Okay, your LHS is EDS. Okay, integral E ds. Now integral EDS is equal to integral rho dV by epsilon naught. Here we used the definition of volume charge density. That's why we studied all these definitions at the beginning of the lesson. Without knowing this, you cannot solve all these problems. You cannot apply Gauss law for all these problems. Right? Now this is okay. Now let us go for this. Okay. Yeah. This is equal to, you see, this is also for every unit volume you have the same charge. So this is also a constant. It's a constant. That's why simply it's a constant. You may put this outside of the integral rho dV by epsilon. say this is equal to, what is rho d? Integral dv, total volume of this original cylinder laying inside the Gaussian surface. Okay, so what is the radius of the original cylinder? R. Okay, so now what will be the volume of the original cylinder laying inside the imaginary cylinder? It is rho pi r square, yeah, by r square L, okay, by r square L by epsilon naught. Okay, so now we have this is equal to integral E dot ds L by epsilon naught. Okay, now okay, I will write here, yeah, integral E dot ds is equal to rho pi r square L by epsilon naught. Now let us go for this LHS part. Yeah, here we have to calculate this surface integral over our Gaussian surface. Our Gaussian surface is having three sides. Okay, it is a cylinder. It is having top and bottom as well as lateral surface. Okay, now where is our ds? Let us write our ds here. Let us draw our ds. Why? Because our p point is here. This is ds. This will be the direction of ds. Okay. Now, so far we didn't wrote the direction of E, because this charge is positively. This cylinder is filled with positive charge. That's why field lines march radially outwards. This is the direction of E. Okay. Yeah. Now we are having how many surfaces? Top, bottom, and lateral. Okay, three surfaces are there here. Okay. For this lateral surface, this is the direction of ds. This is the direction of E. Both are parallel. So we have non-zero integral. Why? Because angle between these two vectors is 0. Okay. And whenever we write E integral E ds cos 0, we are only left with E ds, which is a non-zero integral. Okay. Right. When you consider other two surfaces, top and bottom, see here, this is a surface. Okay. This is one surface here. The direction of ds will be upwards. Here also direction of the surface, this surface will be downwards. Okay, if you take some ds here, it will point downwards. Here it will point upwards. Okay, ds direction will be upwards. Here ds downwards. See now, if you try to evaluate this integral, then you end up with 0. Why? Because you see this ds is downwards. See, now your E is radial. Okay, what is the direction between E and ds? 90 degrees. So for E ds cos 90, you end up with 0. The same thing happens here also. So on this side you have only one non-zero integral, that is integral E ds cos 0. this is equal to rho pi r square L by epsilon. Okay. Now let us simplify this in order to get E. Okay, it is nothing but just E ds pi, because cos 0 is 1. On this side you have pi r square L by epsilon naught. Okay. Now, yeah, here E is same. Okay, for all the points on the surface, so E is a constant. So you may write E outside. So inside the integral you have ds only. On this side you have pi r square L by epsilon naught. Okay. Now what is this ds? This is this integral on LHS part. On the LHS is giving the flux from the imaginary surface or Gaussian surface. Okay. That too, we divided this integral into three integrals. Okay, for three surfaces. Now this integral is referring to the lateral surface of the Gaussian surface. Okay. So what will be this the integral ds? Total surface area of the lateral surface of the imaginary cylinder. What is the radius of imaginary cylinder? Small r. Okay. So then what will be the formula for the lateral surface area? Now you may write here 2 pi r L. Okay, L is the length of the imaginary cylinder. This is equal to rho pi r square L by epsilon naught. Now you do some simplifications. L cancel, pi cancel. Okay, now you have E is equal to rho r square by 2 epsilon naught. Okay. On this side we are having r naught, so here you have to write r. 2r into epsilon naught, 2 epsilon naught r. In the numerator you have rho r square. So this is a formula applicable for the points outside of the cylinder. That means E that is R is greater than R. This applies for the first case. That means this applies for the points outside the Gaussian surface. Okay. Now let us stop with this for today. In the tomorrow class we will be discussing about the electric field inside of this cylinder. Okay, thank you.